Hey there, my name is Haoyan Deng, and I am a second year graduate student here at UF, majoring in electrical engineering. And today I'm going to be doing a presentation about my final project for the class EEL 6825. So it's a project about feature extraction. What I'm going to be basically doing for this project is to extract both temporal and frequency features of an input audio signal using this transform called Gabor transform. So first thing first, a little bit of context here. Audio signal processing has become one of the key sectors of our modern day technology. The application of such technology ranges from the most home use setting, like your smart home devices, such as Alexa or Siri, to large military applications such as radar tracking and audio analysis. Amid the current era of ever-evolving technology, the demand for efficient audio signal processing will only get higher. According to a report by Allied Market Research, the current market share for digital audio signal processing is approximately at $11.06 billion. It is expected to reach $23.43 billion by the year 2027, and the annual growth rate is projected to be at around 9.3%. The expected future market growth and increasing demand has to be coupled with ever more optimized algorithm to fuel the growth. So when it comes to processing audio signals, Fourier transform has usually been the first to come to people's minds. In most basic cases of processing audio signals, only frequency aspects of the signal are taken into the account. Fourier transform allows us to extract those features from a time domain and signal intensity audio signal easily. Most of the time, it's usually very helpful to analyze audio signals purely on the frequency domain, since that takes care of the time element, which is difficult to track. Nevertheless, the basic Fourier transform lacks on the information of the original localization of time regarding each frequency component. The loss of this piece of information causes us to lose track of the timestamp of each frequency we're trying to analyze. Therefore, Therefore, Fourier transform only gives us frequency component information but fails to inform us where those frequency components occur in time. This flaw prevents Fourier transform from successful applications in many applications in which both frequency and time information need to be considered. Those applications include radar detection or music component analysis, where both the frequency of the object and its time matter. Therefore, an algorithm that allows us to analyze both the frequency and time component is important for better processing of audio signals. Gabor transform, in this case, is a very decent candidate to perform this task. So, the basic principle of a Gabor transform is to perform a Fourier window of a certain length sliding over the course of the whole audio signal. This allows the Fourier transform to be focusing on a certain small section of the signal in time domain, and this action of segmentation of audio signal in time domain and performing Fourier signal in each segmentation allows us to understand the frequency features of the signal in small scale. If the segmentation interval is small enough, we can then approximately figure out the time point of that particular neighborhood of frequency components through changing the window length and how fast the window moves over the signal. We can obtain different angles and perspectives of the same signal. So the figure shown in this slide shows an overview of how Gabor transform applies a window to divide a signal into different subsets. So mathematically speaking, there will always be uncertainty between time and frequency resolution of the windowed function. So when the bandwidth of the windowed function gets larger, the duration gets shorter, and vice versa. One of the methods that can be used to calculate the uncertainty bounds is to multiply the standard deviation of both time and frequency domain as shown in the first three equations. And also compare with other similar transforms. Gabor transform has the advantage of having the best resolution on both domains. The following sets of Gabor transform, denoted on the last two equations, shows the Gaussian modulated by a sine signal. So in the equation, Alpha denotes how sharp the window is, and F0 denotes the modulated center frequency of the transform. The window size is determined by the center frequency. To meet the resolution criteria, we substitute alpha with an arbitrary constant y, and then make the time duration of the equation below dependent on the center frequency F0. We will then obtain the finalized general equation for the Gabor transform with normalization and maximum response and frequency. So in this project, the problem that I will be analyzing is to recover the music notes of the input music audio signals and put these notes into music sheet after obtaining the frequency information and also when in time those frequency occurs. I attempt to use the Gabor transform described in the previous section to perform component analysis on the input signals. My approach will be based on the paper that I was researching on. MATLAB is the platform where I will be importing and exporting data to perform the Gabor transform algorithm. The music piece that I use for this particular section to test out my solution to the problem is Handel's Messiah. I only use a very small section of the audio signal from this piece, and the figure that's going to be shown on the next slide is the extracted spectrogram of the input audio signal of this particular music piece. Since the signal that I'm dealing with is a music piece, music has melodies which vary in frequencies and also rhythms and tempos which are very time sensitive. So therefore, it is necessary to get both the frequency information and the associated time steps of that frequency to make a meaningful recreation of the music piece. To recreate the specific notes of the audio signal, I first window and slide the given input audio signal to break it down into multiple segments of fixed length. Then for each segment, I apply Fourier transform to obtain the frequency information of that small segment of input for a complete implementation of Gabor transform. This way, I aim to obtain high resolution for both temporal and spatial components of the signal. So the figure shown on the right side illustrates the example of windowing one section of the input audio signal and the processing of Fourier transform. So for the actual implementation, the first step is to set up the parameters and everything. The simulation and testing of the solution is conducted in MATLAB. The code shown here denotes the setting up of putting the audio signal, which in this case would be the music, into MATLAB for reading and processing. Once we have read in the audio, we calculated its sampling frequency and set its transpose for further processing. And the next step is to get an overview of the frequency spectrum of our music by performing the whole Fourier transform for the whole audio piece. And next part of the simulation is to apply Gabor transform of the audio signal input into the MATLAB. So we're now utilizing a windows with a size determined on the setup to be sliding across the input audio signal. For each iteration of the for loop, a segment of the audio signal is obtained. An ordinary Fourier transform is performed for that segment in each iteration. Once the whole for loop has been completed, we have a group of FFT'd audio signal. The last step is to mark them onto a spectrogram, which is shown in this slide. So this is the final spectrogram of the Gabor transform signal. We successfully extracted both the temporal and time details of the audio. However, the time resolution might not be the best for us to get good readings. We can do some modifications of the setup parameters like filter width, filter translation, or even window size to improve resolution for either time or frequency. So for example, a large filter length or window size will result in large segmentation of signal being captured, yielding in better frequency resolution. However, time accuracy is jeopardized in this case and vice versa. So there's a trade-off situation here when it is impossible to improve both temporal and frequency resolution. The improvement of one of them is at the cost of lowering the quality of the other. So the 9 plots shown in this particular slide show that when we constantly modify the filter parameters, which is also the window parameters, we can change the resolution of either frequency or time, but not both simultaneously. So, once the setup phase is set, we're now experimenting our setup to recover notes from a piece of music. The music that I'm going to be using for this experiment is called Mary Had a Little Lamb, which is a pure piano recording. The reason that I switched from the previous music piece from the previous section is that this piece is less complex and involves fewer musical instruments, and there are fewer notes, since the task here is to recover music notes. We have to convert the frequency obtained from the Fourier transform, which is an angular frequency, to sound frequency, which is in hertz. Applying the same setup used for the previous part, we obtain the following spectrogram on the top for this piano recording. As can be seen from the spectrogram, we can clearly distinguish the frequency elements of our 15-second piano recording from the spectrogram. We have a fairly accurate reading from it. To put the spectrogram in better perspective, I translated it to a dot plot, since each note in music is succinctly represented by a single dot note, which represents a frequency at a given time. And the dot plot or the scatter plot is shown on below the spectrogram. So, based on the conclusions drawn on the figures shown in the previous slide, we can further compile the information into a music sheet with frequency information and time information, which is shown in this particular slide. I have successfully recovered the notes of the piano recording using Gabor transform. So, as a quick recap, throughout this project, I was able to successfully identify musical notes based on the input music audio using Gabor transform. I have been able to simulate the mathematical equations of the transform and apply them to real-world audio signals and extract the frequency and time features of the signal. Finally, I compiled the frequency and time information of that signal into the music sheet as the recreation of the input piano recording. In conclusion, I have learned to use Gabor transform as an effective feature extraction tool for audio signals. By comparing my work with efforts done by other researchers, I was able to recognize the flaws of my design and also the advantages of my implementations of the others. I am also aware that this application is just the tip of the iceberg. The technique of using Gabor transform can be used in various other applications like image processing or radar tracking, and my project only involves the basic 1D application of the technique. Thank you.